So, we've seen in the previous talk how we can describe the diffusion tensor. Essentially, we can describe different diffusion profile by using the three eigenvalues. So, we can have axial anisotropy, we can have planar anisotropy, we can have isotropy just by looking at the three eigenvalue. So this is a quite useful way of describing and compressing information. In fact, with a compact description with three numbers, we can describe quite a lot of the microstructure organization of diffusion. But at the same time, this is quite oversimplified description because what is not encoded in these two eigenvalues is essentially lost in our further analysis. And if we look more in detail at the microstructure, a few examples, we can see that one tensor model, a single tensor, might describe correctly the displacement profile of a single fiber orientation. But when we look at the more complex configuration, just as Alex previously mentioned, for example, crossing fiber, we can see that the displacement profile is much more complicated than what we can see in the diffusion tensor model. Essentially, the diffusion tensor model for you is nothing else than an ellipsoid. So you can stretch, compress, change the shape as you like, but it will always be an ellipsoid, right? So when we look at this profile, we have kind of orthogonal fibers. Your tensor profile will be just kind of a disk. So it will be kind of a plan, what I was explaining before, like a planar anisotropy. And in this case, when we have kind of oblique crossing, we can actually see the direction maximum diffusivity is clearly not pointing in any of the true real fiber orientation. So we have to be careful because when we have a very complex configuration, the tensor is not describing anymore the real underlying anatomy. And we can see clearly this in tractography. For example, if we look at the region here in the corona radiata, we have where the corpus callosum is supposed to cross and branch and reach the latter part of the cortex. It's not doing that because essentially is kind of find the corticospinal tract and stop. And because in this voxel here, this blue box here, you have essentially a dominant orientation, and the dominant orientation in the corticospinal tract. So in terms of fiber density, is the highest, is the dominant fiber here. So you start to have false negatives, so you start to miss some reconstruction, but also sometimes you start to have false positive or fibers that are not real. So we don't have a direct connection between the internal capsule and corpus callosum, but because of this kind of averaging situation in each voxel, sometimes we create breach and actually create fibers that are not real. So we have to be careful about this kind of averaging effect of the tensor model. Also, but the problem is not just in tractography, it's also when you look, for example, at maps. So if you look at this region, here have this coronal view, we have, again, the corona radiata, here it is a low region, a low FA region. And what is it? Is this a MS? Is this a stroke? No, it's just a normal brain. It's a brain, and this is our regional crossing. And because we have multiple fiber orientation with each one of them with very high anisotropy, but crossing in the same place. So on average, the different anisotropy average out, and then we end up with a tensor that are more like a sphere. So how bad is it? It's just this spot with the crossing, and well, let me tell you a story. A few years ago, when actually I started OHBM, someone told me, it's interesting to work on crossing fiber, but really, there are not that many crossing in the brain. Well, that was 2006. Now, a few things happened in the meantime. And now we have many papers, multiple papers, they actually clearly say there are between 70 and 90% of the voxel, and probably this is a conservative estimate, they have crossing. So this is a picture we did in a paper a few years ago, showing essentially an atlas of crossing fiber. So we call NUFO maps, number of fiber orientation. As you can see, the region we were seeing before here, the corona radiata, when it is almost white, is not a region of just two crossing. It's actually a region with three crossing. I'll tell you later which kind of the fiber crossing there, but almost all the brain is a two-way crossing, except the corpus callosum and this small spot here corresponding to the corticospinal tract, this spot here. So we're still not sure actually there is no crossing there, because maybe it's just we are not able to see now with the technique we are using at the moment. But when you look here, when you have this kind of white shade here, you have actually three fibers. So you have the corticospinal tract, the callosal fibers, and the associated pathways, could be the SLF or the arcofasciculus. So yeah, we have a lot of crossing we need to take into consideration when we do our analysis. So this is one of the problems, but crossing is not just crossing. There are other type of problem, and I want just to present another one. It's kind of romantic, with a romantic name. It's called kissing problem. And this is happening when, for example, you have two fibers, or that can happen on the large scale of involving more voxel or actually a single voxel. And for example, here you clearly see that when two fibers get close touch or kiss and then separate, here you have the typical crossing, so the fiber cross in the same region and then they diverge. Now, here is easy to discriminate the two configurations, but actually, if you look at the diffusion signal, this is how it looks like. Oops, sorry. With diffusion signal, we don't have any contrast to discriminate. The signal is actually equivalent between the two configurations. So kissing and crossing are the same. Now, think about tractography now. And what tractography will do? Well, sometimes they go the right direction, sometimes they go stop, or sometimes they go the wrong result. So what can we do to go beyond DTI? What can we do to resolve this problem? Well, the first thing we can do, as Jennifer mentioned in a previous talk, is to look at more and more directions. So we start with what is called high angle resolution diffusion imaging. And the plan is quite simple. We don't want just to measure diffusion in a fixed number of directions just to fit the model, like 6 parameters, 6 direction, 20, 30. We actually want to sample the full angular space of diffusion. So we want to measure on many directions, 60, 90, 100, quite a lot. And the idea is, if, for example, we have a single fiber orientation, this is my, let's say, displacement of water molecules. If I sample along many directions, I will be able to get a kind of a three-dimensional representation of the signal. This is for each voxel. And this shape looks like pretty much like a donut, if you want to have an example. So along the direction of the fiber, you have higher signal attenuation. Perpendicular to the fiber, we have less signal attenuation because diffusion is lower. So with a single fiber, there is no added benefit of that. But the real benefit is when you start to have a crossing, and now you start to see the profile is getting more and more complicated, more complex. So now you clearly understand why just using 3 numbers, lambda 1, 2, and 3 for the tensor, the 3 eigenvalue is not enough, because we are not able to capture this complexity, this kind of different shape here. And so what can we do with this? So that HARDI is not per se resolving any crossing, it's not telling anything, it's just giving us more data to work with. And the first thing we can do to resolve crossing is probably to do a multi-tensor approach. So if a single tensor is good for one fiber, why not to use 2 tensors? Simple. And it's working. It's working okay. Maybe it's not working great, because it's okay when you have 2 fibers, but the first issue you have is you need to know a priori how many fibers, how many distinct fiber orientations you have in each voxel. So you have a model selection issue. So you need to come out with some strategy to know a priori in each voxel which model to fit. Then, if you go more than 2 fibers, things are getting complicated very quickly, because it's very easy to have an ill-posed problem. So you're going to have multiple configurations, essentially explaining the same signal. And you can solve impartialities by imposing very strong constraints. For example, you assume just axial symmetric diffusivity. You can reduce or assume that all the tensors are the same. But if you do that, essentially, you're converging to the concept of, or you'll see in a second, spherical deconvolution or other similar method, where they essentially have a model to describe all the fibers together. So probably the most famous methods like multi-tensor approach is probably the ball and stick from Tim Behrens. The idea is very simple. We simplify as much as possible the signal in a way that what we have here is a single compartment, a single component, just we call the stick, and is essentially a lambda 0, 0 tensor. So we have diffusion only in one direction. And then we have an isotropic component, just the ball. So there is no actual tensor at all, it's just one single diffusivity. So if you have that, you have a ball and stick model. If you want to add another fibers, you just add another compartment like that. So you have now a ball and sticks model, and you can have up to 2 or 3, and it usually is fine. And the benefit is quite obvious. If you look at this picture, you can see you can go from one fiber model, you cannot see the SLF. But as soon as you switch to 2 fiber model, you can actually start to see more component. Why? Because the SLF is not a dominant fiber, it's essentially it's less present compared to, I don't know, the cortical spinal tract, or I think in that region you might have the callosal fiber also crossing that region. So you are not going to see the SLF1 in this case as the main fiber in that region if you don't use a multi-fiber model. But over the year, a kind of a more general family started to be available, and now established kind of a standard for different applications. And all these approaches are based now on what is called orientation distribution function, or ODF. The idea is not to fit a precise number of parameters or a specific model. The idea is to try to estimate a spherical function or this kind of shape, or more general, a kind of distribution, a spherical distribution that tell us how many fibers are available in each voxel. So by looking just at this shape, you can actually see, for example, we have 2 lobes, so suggesting 2 fiber orientation. Since it's a 3D sphere, actually it's pointing in different directions, so we also know the direction. And by looking at the amplitude, we can also come out with some kind of assumption about the fiber density or some diffusion properties. So this was quite successful, and many methods have been developed around these ideas. So on one side, we have what we call the diffusion ODF. And for diffusion ODF, we have all the family related to DSI, QBall, DOT, GQI, etc. And the idea is always the same. Essentially, we want to start from a diffusion signal, do some kind of signal transformation, and use the Fourier relation between diffusion propagator and diffusion signal, and end up with this kind of propagator kind of result, and calculate essentially the radial probability. I'll come back in a second to explain better what is it, but essentially this is the radial probability to have diffusion in all the directions, essentially. On the other case, we have what we call fiber ODF, and essentially this is the result when you do spherical deconvolution or similar approach. And as you can see, again, many people work on this approach. The idea here is slightly different. So instead of just transforming the signal, is also, let's look at the signal, but also let's use a model. And the model is the donut, okay? So if we assume the donut is a good representation of how a signal from a single fiber is coming from, so we can use this to deconvolve the overall signal and extract essentially the weight of the fiber in different directions. And that is essentially fiber ODF. So let's look more in detail at the different defined, because this is quite an important concept, and sometimes people get confused between DODF, FODF, is the same, I'm using an advanced method, that's it. It's not exactly the same. So let's have a look more in detail. So if you look at the diffusion distribution function, what we can see is this profile is more related to actually the displacement profile. So if these are the fiber we see in the previous example, the displacement profile, diffusion, is quite a blur function because the water molecule are not exactly following the direction of the fiber, but they're actually hindered by the fiber. So there is kind of blur profile. And the diffusion ODF intrinsically has this kind of blur in its shape. On the contrary, if you look at the fiber orientation, we are not actually looking at the displacement profile of diffusion models. We are actually trying to estimate directly the underlying fiber orientation. So, and that's what essentially we want if we want to do tractography out of it, okay? And now, I want to make one point. Sometimes people say diffusion ODF are usually model independent and fiber ODF are model dependent. It's true, fiber ODF are model dependent, but also diffusion ODF are in a way model dependent. The moment I'm going to use DODF for tractography, because at the moment I'm going to use the peak of this ODF for tracking, I'm assuming, so I'm essentially putting a model that is the direction of the fiber. So intrinsically, I'm just thinking that is how the fiber is oriented. So that is a model in a way. Okay? So let's have a look at, oops. Let's have a look at some of the different methods. So the first one is diffusion spectral images, kind of the grandfather of the advanced method because it was introduced by Van Vedin in 2000. But actually, if we go back a few years, we can actually say that Paul Callaghan already in 1988 is introduced the concept of using a 3D Fourier transform on Q-space imaging data to extract the displacement probability. So in a idea, Paul Callaghan inspired the DSI, and then Van Vedin actually realized in practice. So the idea is to collect data, not just on these HARDI methods, we just collect diffusion along a Cartesian sampling, so X, Y, and Z, and for each axis we use let's say 10, 5, 15 different Q value or B value. So in the end, we are going to have 10 by 10 by 10, so we are going to have 1,000 of volume very easily. And if we do that, we exploit this kind of relationship between between the diffusion signal and diffusion propagator through the Fourier relationship, we can immediately get the diffusion propagator for each voxel. So if we have this diffusion propagator for each voxel, now we have the exact distribution of water molecule in space. And then we can calculate the radial integral for each voxel, and that is giving essentially the probability of diffusion along the direction. And this is essentially diffusion on the F. So there are different ways of amplify the kind of peaks. You can use, you can change the exponential here, you can use some other trick, but essentially this is the diffusion on the F. The advantage of this method is, as I said, in theory you don't need to assume anything to build this function or to this preprocessing, but at the same time, as I said, we are going to have a lot of volume to acquire in order to get the DSI working. So we need to have 500 volumes, so usually it's taking a lot of time to collect data, and we need very high p-value. So the risk is we might have low SNR at some point. And even if you get 500 volume, you can actually see that other methods with 60 direction can give you the same result, if not even better. So another method can kind of evolve by that is cubal imaging. And the idea of cubal imaging is to do something similar to DSI, but just using a standard HARDI acquisition. So you collect data on a HARDI sample, you apply a Funk-Radon transform, and you get something that is very similar and essentially to a DSI. Many methods have been developed. We start from Funk-Radon, but then there are some kind of spherical harmonic kind of way of describing the signal and calculate this integral. And you can actually improve, get much better result in terms of stability to noise and probably angular resolution. More recently, the Coteau also introduced a way to sharpen, to increase further the idea of the peak of this of the DODF, and we can in a way get something that is essentially a fiber DF. But the point is, if we introduce a model of our diffusion directly on the DODF, why not to do that directly on the signal? And essentially, this is spherical deconvolution. That we are doing this kind of sharpening, but starting directly for the signal without passing to the diffusion of the F. So how spherical deconvolution works? Well, the idea of spherical deconvolution is quite simple, as I said. Everything starts with the model. The model is this kind of fiber response, and is essentially our donut. Take a donut, and we see how, looking at the signal, so we can see a signal, for example, two fiber can be see as a sum of two fiber, can be also see as a convolution of this model, the donut, and a fiber orientation. Normally, what we have is the signal. We can assume, we can choose a model. We can sample the model from the signal, so we can select a voxel with a single fiber orientation, or we can actually, that's why I usually prefer to select a model directly from some parameter, I estimate, and then we can do the deconvolution. So the idea of spherical deconvolution is essentially deconvolving the signal, assuming a model of the fiber, using this fiber response. Many methods have been applied, and I'm not going to show you all of them, I just give a couple of them. But the overall kind of theme during the year was always try to increase the angular resolution while at the same time try to control the instability, because spherical deconvolution is an inverse problem and is very sensitive to noise and instability. So this was the beginning. So as you can see, if the middle, this kind of little dot here, it was kind of the mean result, and this was the kind of variance of those different noise runs. You can still see at the beginning we're not stable at all. Over time we increase in terms of stability, but we have problem with kind of angular resolution, and a little by little we also get better on both. So the first method I want to talk about is CSD, or constrained spherical deconvolution. Probably is the most known spherical deconvolution approach. And the idea is to introduce some kind of, using spherical harmonic and some non-negative constraint to try to extract the fiber orientation. It's working pretty well, and it can work, particularly for high B value, is quite good. But when you start to have lower B value, or you have some problem with the fiber response, it starts to generate some kind of spurious spike. To improve on that, there is a work from Chantal Tax actually using a calibration. You can iteratively optimize the fiber response for your data so you can compensate for this issue. Another property, something I worked for a few years on that, is the Richardson-Lucas spherical deconvolution method. And the idea is we took Richardson-Lucas is a well-known astronomical algorithm for image restoration, and is particularly robust to noise, is robust to fiber response, so it doesn't need to know the exact fiber response to get a reasonable answer, and most important is intrinsically give you a non-negative constraint. And this is exactly what we want for the diffusion problem. So how we start? We start from a signal, we start from a kind of isotropic first solution, and through iteration we actually end up to get a pretty good estimate. This is a noise data, it's not for noise-free example. So it's a nice algorithm, quite simple to implement. It is a global convergence. So there are many nice features if you want, you can read in these papers. But just solving spherical convolution is not all the problem. You want to go more in detail. So if you want to do tractography, you want to be sure the fiber orientation you get are the realistic one. And one thing we noticed that if you assume spherical deconvolution, you essentially assume that all your signal is coming from white matter. But in the brain, you have gray matter, CSF, edema, lesion. So you need to take into account the presence of other contributors to your signal. So what we did in a sort of an update version of the algorithm, we also introduced regularization that by kind of penalizing low amplitude peak and leaving intact the higher amplitude, we're actually controlling for partial volume with other tissue, and actually improve a lot the stability of the metal in the presence of partial volume. So as you can see here, in the white matter region, there is no difference essentially, but when you go into gray matter, you actually get a more kind of smooth solution telling you, look, there is not a dominant fiber orientation in this voxel. So many methods have been proposed. There has also been a comparison recently between the CSD and Richardson-Lucas. This is not to mention, this is not to actually say which one is the best, but just want you to show you that actually, depending what you want to do and depending the configuration of your data, you might actually have different results if you use this different method. And for example, here, if you have an error in your fiber response, for example, you're assuming a very sharp fiber signal, but your signal is quite low with low anisotropy, well, CSD might start to generate quite a lot of false orientation in direction, systematic in direction that are not the direction of the fiber. So you can actually have a 90 degrees, 45 degrees, 33 degrees. This is kind of a systematic error you have from CSD because the model is very sensitive to error in the fiber response. On the contrary, Richardson-Lucas doesn't have this problem, so it's not generating false direction, but it's going to give you a more blur profile. So we are going to lose something else. So we are going to lose angle resolution. So we are going to resolve less crossing. So that's a trade here. Better to see more crossing, but wrong, or better to see less crossing, but more realistic. Leave it to you. So I prefer the second one. So yeah, and that's why, because this is an example of tractography when you do multi-fiber orientation. So as you can see on the left, you have a beautiful corticospinal tract. On the right, you have a beautiful genius. Clearly, it's not, okay? So the reason is, this is an example of doing tractography with advanced modeling, but without putting any constraint on, for example, angle, anisotropy, amplitude, FOD. So what I want to show you is, for many years, we work on advanced method to resolve crossing, but resolve crossing is not the only problem. You want to resolve crossing, one, you want that the fiber are realistic. And then you also have to consider when you do tractography, because you have more fiber to choose, you have more chance also to get it wrong. So now new tractography algorithms need to be more carefully developed to take into account all these issues when you do tractography. And just to give you an example, so moving from DTI to spherical deconvolution, as Alex showed before, now you can clearly see more information in this voxel. So you can see multiple fiber orientation, you can see U-shaped fiber, you can see multiple dominant fiber in the same voxel, and thanks to also the improvement of acquisition. So for example, if you have multiband now, you can collect 60 direction, B1500, B3000 in 4 minutes, 5 minutes maximum. So there is a lot more we can do with diffusion now with the new technology. And yeah, and this is and this is an example of what you can do with this advanced model. Again, you can clearly see that Now we can click across all the cortical spinal tract. We can see the lateral projection of corpus callosum, but also some of the typical artifacts. You have the lower part here of the pons are gone, and now we can actually see the right cortical spinal tract. Right, so this was kind of the standard for the last 3-4 years. And now, as I said, with the development of new hardware, the new acquisition sequence, we are starting to have a lot more data to work with. And I think one of the things we need to take into account the next few years, we are going definitely to work on multi-shell data. And this is an example, is an evolution of CSD, taking into account of multi-shell data. So you can actually decompose the signal from white matter, gray matter, CSF. Now you can have more things to work. You can separate the different contribution, and you can actually improve the ability to detect fiber orientation without the spurious peak I was telling you before, because you have partial volume. Now the thing is actually, because again, we are going to have a lot more data, the model independent approach, what I was saying before, DSI, have been kind of, have evolved, and now we have methods like the mean parapropagator or map MRI, able to extract a lot more information in a model independent way. So you can actually have propagator anisotropy, you have a kurtosis measure, and also you can start to get to some ODF that are very sharp and very interesting. So again, many new methods are exploding now and coming out. So you can go from a DTI, now you can go to a very multi-tensor map MRI. We can have very sharp fiber orientation. So there's kind of interesting thing happening at the moment in the field here. The last thing I would like to talk about modeling is about asymmetric FOD. So if you look at the signal, if you remember the first talk, we know that diffusion signal by definition is symmetric, but anatomy is not. So if you look at this voxel here, so this kind of histological slides, you can see there is kind of fanning structure. So you hear very compact and you fan out in the jar. Well, if we look at the signal and we calculate the FODF, that's what you're getting. You're getting a shape like that. So it's a fanning by symmetric in both directions. Now, if you look and imagine we can get something more realistic anatomically, we would like something like that. So we want fanning only when we go from here to here. We want to fan out to get to the cortex. But when we start from the cortex, we want to get sharp inside the gyri, okay? And actually, there are a few methods coming up at the moment. One is from Marco Reis and one from Bastiani, just in press. They're actually starting to calculate this asymmetric for this. This will be a very big improvement if we can see that, if we can actually prove that these methods are working. They are just so new, there are no real application we are yet using this method. But there is a lot of that can be done with this kind of idea. Okay, so the last thing I want to talk about, we can solve crossing, we can better model the fibers, but what about metrics? Can we do some quantification? Everyone normally working with FA, mean diffusivity, or some kurtosis matrix, but all these metrics are all voxel-based. If we have multiple fiber orientation, can we split this information across depending on different fiber orientation? And yes, we can. There are different approaches. More or less, they're all based on the same ideas. One is called orientation isotropy, apparent fiber density, angular fiber density. But the idea is always the same. Essentially, we want to decompose and look at kind of the amplitude of or the integral of the whole lobe and see how this is affected by different biological changes. For example, here, if we simulate a fiber degeneration, let's say one of the fiber lose fiber volume fraction or increase in radial diffusivity, assuming demineralization, what we can see is a clear decrease on anisotropy, while the other one stay the same. This is pretty interesting because we can decompose between healthy and pathological fiber within the same voxel. If we look in comparison to the tensor, you can actually see just a slight rotation of the tensor, and sometimes not even a significant change in the phase. So this is something I think is really interesting, and we need to work more in this direction. So just to give you an example, so you can see the amplitude of the FOD or other methods are rich. So we can use this information to do some analysis. And for example, if you look here, you can see the clear difference between a voxel-based analysis and a track-specific analysis. So FA will be always the same. If you map FA on a two-fiber crossing, it will always be the same for the two fiber. For example, here, arcuate and corpus callosum. But when we look at the fiber-specific matrix, you can actually see different value assigned correctly to the different fibers. So low density of callosal fiber crossing with high density of arcuate fascicular fiber. And this is something that can actually represent healthy versus pathological fiber crossing in the same region. Okay, so take-home message for my talk is definitely the white matter is more complex. The diffusion tensor model is good as a starting point, but if you really want to disentangle the complexity, you need definitely to use more complex model. And yeah, we've seen there is a lot of crossing in the brain. We can solve the crossing now, this is well established. And we are starting also looking at fanning, kissing, bending, using this kind of potentialities asymmetric FOD. We still don't know how well this method are working in practice, but finger crossed. And I want to stress this is very important. Diffusion of the F of the F, they look similar, but they are different, okay? Remember that in one way we are talking about diffusion displacement, the other way we are talking fiber orientation. And usually it's much easier to get F of the F with lower B value compared to D of the F. Finally, when you do tractography, you don't want to just get crossing fiber. You just want to be sure that your fiber orientation are reliable. So it's very easy now with advanced method to get really random track, okay? And when I talk in my talk essentially of models, but it's not just a problem of model. It's always a balance between quality of the data, time available for your study, and model you choose. For example, here we have a singulum done with ETI more than 10 years, more than 15 years ago now. This is spherical deconvolution, and this is other methods using also advanced model, but because they use a very low spatial resolution, like 3 millimeter, 4 millimeter, they are not even able to visualize the full singulum. So the fact you're using an advanced methods doesn't mean you always get the right result. So always balance between what you're doing, and you want essentially the best quality data for your analysis. And finally, never forget about the spatial resolution. I'm sure that maybe Maxime later will talk more about that, but spatial resolution is important limitation from tractography. We know there is a lot of stuff going in the same 2 millimeter or 3 millimeter or 1 millimeter voxel, and sometimes we cannot disentangle it correctly. And I think that's it. Thank you very much.